Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is power. Our objective today is to take a close look at the different permutations of power calculations for DC electricity, sometimes collectively known as Watt's laws. We'll review power and energy, and use power figures to error check calculations and to troubleshoot basic electrical circuits. Additionally, we'll introduce a device used to measure power known as a wattmeter and have an early low-level discussion of transmission and solar power. Power is a pivotal concept for this series and serves to unify a number of previously independent topics. As such, expect numerous shout-outs to previously covered material. If at any time you are presented with material you have never seen or only dimly recall, please take the time to click the provided links to come up to speed. Recall during the Energy and Power lecture, available at the Big Bad Tech channel, our first shout-out, I introduced the general concept of power, where power is the time rate use or production of energy. Expressed mathematically, power is equal to energy divided by time. Energy can take many forms, but is most easily conceptualized as applying a force a certain distance, where energy is force times distance. If I move an object that resists me with 5 newtons of force, a total distance of 4 meters, I've done 20 newton meters of work, where a newton meter is equivalent to the SI unit of energy, the joule. Stop right here and just think of every single joule of energy as a piece of firewood. In this case, 20 pieces of firewood got loaded into this system. We'll come back to the purpose of this visualization in a moment after we deal with the dim-witted savages who don't use the metric system. If you want to use archaic and unwieldy units to describe energy, you could move an object that resists you in units of pounds force, a certain distance in feet. Energy is still force times distance, so the derived energy unit is a foot-pound force. If 5 newtons is roughly equivalent to 1.124 pounds force, and 4 meters is roughly equivalent to 13.123 feet, we've put 1.124 pound force times 13.123 feet, or 14.75 foot-pounds force of energy into our system, where 20 joules of energy is roughly equivalent to 14.75 foot-pounds force of energy. How fast you get this energy into or out of a system is power. Power is the time rate expenditure or production of energy. Power is energy per unit time. Returning back to our pieces of firewood visualization, think of the chores you did as a kid. Those individuals in temperate or tropical climates have no idea what I'm talking about, but those of you that do are intimately familiar with the never-ending chores of cutting, splitting, stacking, and hauling firewood. This task often falls to the eldest child and is their responsibility to ensure the family makes it through winter alive. This does not mean the task is always approached with vigor and potency. Quite often, there is an associated amount of moaning and whining accompanying this task. If you as a child have ever been locked outside your house in the middle of a winter storm at night, like I have, more than once, and been told to bring in 20 pieces of firewood before your parents will let you back in, you've got one of two options. One, you can mope and whine and drag your feet and just pick at the task and take a long time to do it. Or two, just go get 20 pieces of firewood as quickly as possible in the shortest amount of time possible. Either way, that door would not open until there was 20 pieces of firewood on the front porch. The task required a certain input to complete, and it was my choice to accomplish this task powerfully in a short amount of time, or less powerfully over a long period of time. My parents aided me in this decision by often locking me outside the house without a coat, at night, in the middle of a storm. Just kidding. They actually made me bring in 40 pieces of firewood. Anyways, the purpose of this diversion was to clearly delineate between power and energy. Energy was the growing pile of firewood on the front porch. How fast I got that pile there was determined by how powerfully I did the task. Power is the time rate production or consumption of energy. Anyways, let's say a 20 joule task was accomplished powerfully in 1 second, and a similar 20 joule task was accomplished less powerfully in 10 seconds. Power is energy per time. The first task power input was 20 joules in 1 second. If a joule per second is a watt, our power input was 20 watts. Our second task power input was 20 joules in 10 seconds, or 2 joules per second, where a joule per second is a watt. The same 20 joule task was accomplished in less time with a more powerful 20 watt input than it was with a less powerful 2 watt input. It makes sense. Now, let's tie this power and energy relationship with our basic electrical quantities of voltage and current. Recall during the Basic Electrical Quantities lecture, available at the Big Bad Tech channel, I introduced electrical power, where electrical power is typically calculated using the product of voltage and current. Using shorthand, I could say P equals V times I. The unit of power is watts, the unit of volts is volts, and the unit of current is amperes. Realize both the volt and the ampere are derived units, where a volt is 1 joule of energy per coulomb of electrons, and an ampere is 1 coulomb of electrons moving by a point in 1 second. A coulomb is just a group of electrons, kind of like a dozen eggs, but it's a lot bigger than a dozen. If this group of electrons has a voltage by virtue of its position, the same group of electrons is carrying energy, quite like carrying an armload of firewood. The more voltage that group of electrons have, the more firewood that group carries. The group of electrons have energy. That's voltage. Now make the group of electrons move into or out of a system. That's current. If the group moves fast, that's a lot of current, and a lot of energy is dumped into a system in a short amount of time. If the group moves slowly, energy is slowly input into the system. If the current is sustained, group after group of electrons arrives, each dumping its associated load of energy into the system. The time rate of energy arrival is power. The growing pile is energy. Using the units to aid us, we realize that our power equation of voltage times current simplifies to a joule per coulomb times a coulomb per second. And the coulombs cancel out to yield a joule per second, or energy per unit time, where a joule per second is the SI unit of power, the watt. Electrical power delivered to a system is the source voltage times the current supplied by the source. This is our power input. Electrical power consumed by an element is the voltage drop across the element times the current through the element. This is our power output. In the case of a single source in a circuit with a single element, where the system is 100% efficient, an obvious oversimplification, the power input to a system is always equal to the power output by a system. This is not really far from the truth for simple DC systems and resistive elements. The losses that do occur are pretty negligible in comparison, but we can expand this to include losses where power input equals usable power out plus losses. The ratio of usable output obtained per unit of input is known as efficiency, something we previously covered in the efficiency lecture available at the Big Bad Tech channel. Your definition of usable and lost power may vary from one application to the next. A motor produces useful mechanical output, but gets hot while doing so. In the case of a heater, pretty much all the power input to a resistor is dissipated as heat output anyways, so the losses would be trivial enough to warrant dismissal. For the purposes of calculations, I'm lumping my losses into my output. This simple understanding of power in always equals power out relationship is quite possibly the single most useful means of error checking calculations. I know the circuits I'm presenting to you now are single sources and single elements, but it's not going to stay that simple for long. Pretty soon you're going to have to deal with different voltage drops, different currents, even different sources. But when it's all said and done, power input always equals power output. This means you can't get more power out of something than you put into it. It'd be nice, but you can't. It also means all input power has to come out somewhere. The reason why this power in always equals power output relationship is so powerful for error checking calculations is because you're coming at your calculations from two different perspectives, the source side and the load side. If the voltage supplied by the source times the current coming out of the source is 100 watts, and you calculate the power dissipated by the system to be 80 watts, your calculations or your observations or both are wrong. Power in always equals power out, and they must meet in the middle. This property becomes increasingly important as we crank up the complexity of our circuits. The power equation for DC circuits is very simple. If it's a source, it supplies power equivalent to the source's voltage rise times the current supplied by the source. If it's a passive element within a circuit, the power dissipated by the element is that element's voltage drop across it times the current through that element. In theory, this seems easy, but in practice, power measurements are kind of a pain. The reason it's such a pain is that you have to take two measurements, voltage and current. This would necessitate two measurements with two different instruments, a voltmeter and an ammeter. Recall from our Ohm's Law lecture, available at the Big Bad Tech channel, there exists a relationship between voltage, current, and resistance. We could perhaps unify this Ohm's Law concept with our power equation and find alternate permutations of our power relationship that might prove more useful in practice. I'm not saying you're going to get out of taking measurements, but I am saying certain measurements are substantially easier to take than others. Voltmeters are easy to use. Resistors have the value written right on them. Current is a little tricky. I'll show you the trick to measuring current using an ammeter in the lab practices lectures, but it's still not pleasant by any means. Consider the unpleasantness of taking two measurements. Let's say a 120 volt source is supplying current to a common incandescent bulb modeled as a 144 ohm resistor. We would ordinarily have to use an ammeter to measure the current, or use Ohm's Law, where current is equal to voltage divided by resistance. 120 volts divided by 144 ohms would yield approximately 833 milliamperes of current going through it. Now, knowing 120 volts was dropped across it and roughly 833 milliamperes was flowing through it, via the power equation, power equals voltage times current, 120 volts times 833 milliamperes yields 100 watts of power. This took a two-step calculation or necessitated both a voltage and a current measurement. Look at the setup statement for the scenario. We already know the voltage. We already know this bulb has a 144 ohm resistance value. Can't we just unify Ohm's Law in our power equation to perhaps cut current out of the picture? I believe we can. If power equals voltage times current, and via Ohm's Law, current equals voltage divided by resistance, we can substitute this into our power equation, where power now equals voltage times voltage divided by resistance, simplifying to voltage squared divided by resistance, simply by taking the voltage drop across the resistor, or the voltage supplied by the source, squaring it, and then dividing this value by the resistance value, we can determine the power dissipated by this bulb with no current measurement necessary. This is a major time saver. At no point do we ever need to measure nor calculate current. Neat, huh? But what if we did know the current though? Can we cut voltage out of the picture? I believe we can. If power is equal to voltage times current, and via Ohm's Law, voltage is equal to current times resistance, we can just substitute this into our power relationship, where power is now current times resistance times current, simplifying to power is equal to I squared times R. If we observe 833 milliamperes flowing through a 144 ohm resistor, we realize this resistor is dissipating 100 watts. Again, quick and to the point, necessitating a single measurement. Here's what's really neat about these different permutations of the power equation. You would not even need to look at the voltage supply if you're reading your ammeter. Just crank it up until the ammeter hits 833 milliamperes and the source would be at 120 volts, because that's the voltage that would supply 100 watts to our system. Power is equal to voltage times current. Power is also equal to voltage squared divided by resistance. And finally, power is equal to current squared times resistance. See how the recursive nature of the power in always equals power out relationship is super handy? It always wraps back on itself, and you can use this fact to quickly and efficiently arrive at the results with very little need for repetitious measurements. Consider alternate permutations of these three different power relationships. Let's say we know power and voltage, but don't know our current. What's the current supplied to a 25 watt CFL bulb if it's being supplied by a 120 volt source? This is easy. Power is equal to voltage times current. We know the power. We know the voltage. We want to solve for current. Divide both sides by voltage. Voltage cancels out. Current is equal to power divided by voltage. 25 watts divided by 120 volts yields roughly 208 milliamperes of current. This again points to the clear superiority of the CFL over the incandescent light bulb. Not only is it using less energy over time because the instantaneous power consumption is less, it's doing so because it's drawing less current. If something draws less current, the size of the wire can be smaller. Now, what's the resistance of this same 25 watt CFL? Using the relationship power equals voltage squared divided by resistance, we can invert both sides to get resistance on the top, multiply by V squared both sides, where V squared cancels out on one side, and resistance is equal to voltage squared divided by power. 120 volts squared divided by 25 watts yields a resistance of 576 ohms. Check your work using Ohm's Law. What is the current drawn by a 576 ohm resistor if there is 120 volts across it? Current is equal to voltage divided by resistance. 120 volts divided by 576 ohms of resistance yields a current of roughly 208 milliamperes. Oh my gosh, it's the same value we calculated earlier. Again, this power relationship is incredibly versatile and handy in checking and double checking your work. This is like making a burrito. You can make a burrito with rice, beans, carnitas, and salsa, or you can make one with carnitas, rice, salsa, and beans. Or you can get totalmente loco and make one with frijoles, salsa, arroz, y carnitas. Either way, you're going to get a burrito that is 100% delicioso. It doesn't matter where you start, and it doesn't matter which direction you go, you are going to arrive at the same results every single time. If one path is blocked, there are numerous alternate paths that will take you to your intended destination. The results should be correct, and they should be in accordance with your observations. You are limited only by your creativity. This is a scary feeling for button pushers who want to be led to the next button, push it, and then be led to the next button, push it, and move on. This isn't button pushing, and I am not going to waste my time or yours to show you how to push buttons. This is art school, and I'm going to give you some power tools and just sit back and let you create. Can you dig it? That's the purpose of a hardware lab. Find the methods that work best for you. Develop your own style of problem solving and troubleshooting. Get good at it. Get efficient, and don't make mistakes. If I present you a method that you totally suck at, practice it more, or just plain don't use it. Use a method you're good at. Use methods you like using. My only demand is that you get correct results in the quickest manner possible. Again, you are limited only by your creativity. Try not to be scared. Experiment with everything. In this spirit, I present to you what I like to think of as the grand unified theory of power, sometimes collectively known as Watt's laws. Here's a visual aid that presents all 12 permutations of both Ohm's law and the power equations to solve for 4 properties: voltage, current, resistance, and power. I sincerely doubt you'll be able to memorize all 12 permutations in their respective positions on this disk, so do not even try. It's a total waste of your time and something button-pushing drones like to do. If you've got basic algebraic manipulations down, you can use the quick and easy Ohm's Law pyramid and the power equations to arrive at any value you seek using any combination of inputs. No sense in carrying all the tools in your toolbox when you commonly use only some of them, and some of them can perform dual tasks. All the visual aid serves as is a touchstone to make sure you're doing algebraic manipulations correctly. Again, this isn't button pushing. You need to be flexible and use base skills like algebra to lighten your load. This doesn't mean you shouldn't have the Watt Laws circle prominently written on the back of your notebook or scientific calculator. It's a visual aid only, and one of these days, someone's going to take it away. Be flexible. use the Ohm's Law pyramid and the 3 different permutations of the power equation and algebra as your tool set. Let's let you off the leash a little bit here and try some illustrated example problems. Pause the lecture and see if you can use the given values to solve for the desired unknowns. Do not button push. I took the Watt's Law circle away for a reason. I know you can just rewind or look at your notes, but resist the temptation to do so. Try just using the Ohm's Law pyramid, the 3 power equations, and basic algebraic manipulations to solve for these quantities. You'll be glad you practice it like this if you ever come across a similar circumstance when you're in a lab environment, at work, or during a test. Hint, hint. Example 1. What is the power supplied by a 12-volt battery when it draws 150 amps of current to start a car? Power is equal to voltage times current. 12 volts times 150 amps yields 1,800 watts, or in proper engineering format, 1.8 kilowatts. Example problem 2. What is the current draw for a 15-watt compact fluorescent light bulb supplied by 120 volts? If power equals voltage times current, via algebraic manipulation, current equals power divided by voltage. 15 watts divided by 120 volts yields 125 milliamperes of current. Example problem 3. What is the voltage necessary to supply a 480 watt device with 20 amps of current? Via algebraic manipulations, voltage is equal to power divided by current. 480 watts divided by 20 amps yields 24 volts. Example problem 4. What is the power dissipated by just the line when that line consists of a mile-long 12-gauge wire with 1.588 ohms per 1,000 feet when it carries 9.3 amps of current? I've not directly given you the resistance value, but can be easily calculated using some unit conversions, where 1 mile equals 5,280 feet. And if the wire has a resistance of 1.588 ohms per 1,000 feet, 5,280 feet would have roughly 8.4 ohms of resistance. Power equals I squared R, 9.3 amps squared times roughly 8.4 ohms would yield roughly 725.2 watts dissipated in the line alone. If we wanted to minimize the power dissipated in the line, we'd have to find a substance with an incredibly small resistance to deal with that long length. Or perhaps we could keep it as a short length. But a far better means of doing this would be to somehow find a way to reduce the current. Because again, power dissipation is a function of current squared. We'll come back to this in a little bit when we deal with transmission lines. Example problem 5. What is the resistance of a 9 kilowatt boiler that draws 37.5 amps of current? Via algebraic manipulation, we realize that resistance is equal to power divided by current squared. 9 kilowatts divided by 37.5 amps squared yields a resistance of 6.4 ohms. Example problem 6. What is the expected current draw for an 800 watt toaster with 20 ohms of resistance? I'm going to take the unusual step of actually doing the algebraic manipulations for you in case there's any questions. We're going to use the power expression power equals current squared times resistance. And we're going to attempt to solve for current, given we know power and resistance. I'll divide by resistance on both sides, where resistance cancels out on the right, and we're left with power divided by resistance equals I squared. We need to continue our algebraic manipulations one more step by getting rid of the squared term, which means we need to square root both sides. On the right-hand side, a square root of I squared is I, where the current draw is now equal to the square root of the power divided by the resistance. Take time to notice that the square root covers both power divided by resistance. It is not square rooting just the power. Use the expression current is equal to the square root of power divided by resistance. Square root of 800 divided by 20 is the square root of 40, or roughly 6.3 amps of current. If you've come this far doing the algebraic manipulations, it'd be a terrible shame to fat finger this thing on a calculator and get a bad answer. Example problem 7. What is the power dissipated by a 430 ohm resistor when a voltmeter indicates there is 8.4 volts across it? Power is equal to voltage squared divided by resistance, where 8.4 volts squared divided by 430 ohms yields approximately 164.1 milliwatts of power dissipated by this resistor. Example problem 8. What is the voltage necessary to dissipate 1.5 kilowatts of power in an electric heater with 9.6 ohms of resistance? Trusting you did the algebraic manipulations, you'd realize that voltage is equal to the square root of power times resistance, where the square root of 1.5K times 9.6, which is the square root of 14,400, or 120 volts. Finally, last one, example problem 9. What is the hot resistance, meaning when it's drawing current, of a 100 watt light bulb when it's supplied by 120 volts? Using algebraic manipulations, we find that resistance is equal to voltage squared divided by power, where 120 squared divided by 100 yields 144 ohms of resistance. Alright, now that we did some illustrated example problems, you should be well versed in power calculations. If that last section left you in the dust, by all means rewind and take a stab at them again. Again, it's often not the electrical concepts students struggle with, but rather the algebra and the numerical literacy that hinders forward progress. As general study skills advice, figure out what the problem is before you go see somebody. No sense in practicing something you already know. Get to the root of the problem quickly and move on. Is it math? Is it the numbers? Is it the electrical concepts? Seek help on that topic and that topic alone before you move on. Let's quickly discuss troubleshooting an electrical circuit using the power relationship. Admittedly, this is not going to be of great use to us at this point despite all the earlier hype. The reason so is because our circuits are very simple right now, often consisting of one element, and it's kind of hard to mess up one thing. Students try, but it takes a concerted effort to do so. Regardless, consider a situation where a 20 volt power supply indicates it's in overload every time you power it up when it's hooked up to a single 1 kilo ohm resistor. I know we haven't gone into detail about power supplies yet, but realize power supplies are limited to the amount of power they can supply. Most power supplies are current limited, meaning there's a certain maximum current it will output, beyond which current just flatlines at a preset value. If your circuit draws in excess of this level, the power supply just says overload and refuses to supply additional current. This is a good thing and has saved many basic electronics students a swift boot in the backside for setting their lab station on fire. Let's say we set up our power supply to supply 20 volts to a 1 kilo ohm resistor, and our power supply is current limited, meaning it maxes out at 800 milliamperes. As soon as we turn it on, the current spikes to 800 milliamperes. Overload. What's the problem? Well, first off, you don't even know what to expect because you didn't do your calculations. You got to know what to expect. What's the current you would expect to be drawn by a 1 kilo ohm resistor when it's hooked to a 20 volt source? Current is equal to voltage divided by resistance. 20 volts divided by 1 kilo ohm yields 20 milliamperes of current. What could we expect the power to be dissipated by this resistor? Power is equal to the voltage across it times the current through it. 20 volts times 20 milliamperes means this resistor would dissipate 400 milliwatts of power. Let's say this resistor has a 1 watt power rating, and we're clearly inside this range. The problem is we are not observing our expected value. Our power supply is delivering 800 milliamperes to our circuit. You might rush to judgment that the 1 kilo ohm resistor is drawing all 800 milliamperes, but that is not the case. Power equals current squared times resistance. 800 milliamperes squared times 1 kilo ohm would mean this resistor would be dissipating 640 watts of power. Yet the resistor is sitting there, clearly not on fire. You want more proof something is awry? If the 1 kilo ohm resistor was really drawing 800 milliamperes, we can use Ohm's Law to figure out how much voltage would be necessary to supply this current. Voltage is equal to current times resistance. 800 milliamperes times 1 kiloohm yields 800 volts. Something is terribly wrong and nothing makes sense. Or does it? Recall, our power supply is current limited. Use Ohm's law to determine why the current is unusually high. An unusually high current is indicative of a low resistance path. Can you figure out what is wrong with the circuit now? There's an errant short in parallel with it. Either some extra wire is in there, or you're using your protoboard incorrectly. If you took a voltage reading across this resistor, you'd not find 800 volts, nor even 20 volts, but rather a very, very small voltage because our power supply is current limited. Current is the effective voltage. If current is high because of low resistance, the power supply simply lowers its output voltage until it reaches that preset current maximum. Let's assume our short in parallel with our 1 kilo ohm resistor is not 0, but rather something very small, on the order of 1 ohm. The total resistance of a parallel combination of a 1 ohm resistor and a 1 kilo ohm resistor is, for all intents and purposes, still 1 ohm. Using the idealized combination of these two resistors in parallel, we realize the source is only seeing 1 ohm of total resistance. What's the voltage necessary to draw 800 milliamperes with only 1 ohm of total resistance? Again, via Ohm's law, voltage is current times resistance. 800 milliamperes times 1 ohm yields approximately 0.8 volts. Again, an extremely small voltage because our opposition is low, yields our maximum permissible current draw of 800 milliamperes. You are understanding that power in always equals power out, and your manipulations of Ohm's law can be used to resolve such seemingly unresolvable contradictions. These relationships and laws are always true. The point is, don't rely on just one set of measurements. Look at the power supply when it's overloaded. Don't look too long though, because you're obviously in boot in the backside territory. Just look at it quick and turn it off. I know you set it for 20 volts output when it was not loaded, but when it's overloaded, the voltage should drop to 0.8 volts and the current should peg out to the preset maximum of 800 milliamperes. Even if there's no visual output on the power supply, use your DMM to measure the voltage drop across your resistor and the current through it. Do not for a moment think that your lab partner is not fiddling with the knobs and randomly pushing buttons when you're not looking. Again, trust no one. The thing that you can trust is that power input always equals power output. Another common power-related problem students run across in lab environments is simply overshooting the power rating of devices. I purposely do this in a controlled, safe environment so students get a chance to see things ignite and explode. Seriously, who doesn't like a good explosion? Point is, know what to expect before you build your circuit. In addition to Ohm's law calculations, do the power calculations first. Is it safe to use a 200 ohm resistor with a 1/4 watt power rating hooked up to a 20 volt source? If power is equal to voltage squared divided by resistance, 20 volts squared divided by 200 ohms yields 2 watts. No way is that safe. That 1/4 watt resistor is going to light up like a Metallica concert. At minimum, we need a resistor with a 2 watt power rating. However, is it wise to use a 2 watt resistor? Probably not. I think my car can maybe go like 120 miles per hour, but only in extenuating or really fun circumstances do I attempt this. Ordinarily, I drive it well inside its intended performance envelope. A general rule is to use components with power ratings twice that of anticipated conditions, so maybe a 4 watt resistor would be fine. Sometimes manufacturers specify power ratings even 4 times greater than that of anticipated conditions for systems requiring unusual robustness, like those operated in harsh environments or those with important safety considerations. Regarding measurement of wattage, ordinarily we have to resort to taking both a voltage measurement and a current measurement, or use one of our other permutations of the power equation to do so. Then we'd have to take these observations and perform some math to arrive at our power value. For example, we'd have to multiply our observed voltage drop across this element by that of our observed current through this element. You'd have to use your DMM in two different modes and perform some math. There exist, however, special purpose meters designed for single-step measurements of power where no calculation is necessary. Since a voltmeter measures volts, an ammeter measures amps, and an ohm meter measures ohms, a wattmeter is a device used to measure power in units of watts. A wattmeter is kind of like a box with 2 meters inside. There are typically 2 input terminals and 2 output terminals. The 2 meters inside the box are obviously an ammeter and a voltmeter. The ammeter measures current through our element, and the voltmeter reads their voltage across it. Additionally, there's a little dude in there. Seriously, there is. And he just looks at the voltmeter reading and looks at the ammeter reading and then multiplies them together using his tiny little scientific calculator and writes this value in watts on the screen. Be aware you might run across 3-terminal wattmeters where the bottom terminal serves as a common terminal to the input and output pairs. Again, consider the placement of those meters inside that wattmeter. Voltage was being measured across. Current is measured through something. The wattmeter kind of just serves as a single bridge between our input and output if our only measurement concern is wattage. Bring this discussion of electrical power back full circle. Let's again review the relationship of power and energy. Power is the time rate expenditure or production of energy. Power is energy per unit time. It stands to conjecture then that energy is power applied for a period of time. Energy is power times time. How much energy does a device drawing 2 amps from a 120 volt source use over 10 hours? The answer is surprisingly simple. Energy is power times time. A device drawing 2 amps from a 120 volt source would dissipate 120 times 2, or 240 watts. If this 240 watts was used for 10 hours, it would use 2,400 watt hours of energy, or more appropriately, 2.4 kilowatt hours. The kilowatt hour is a unit of energy. It is not a unit of power. I know there's a watt in there, but look at it. It's power times time. The pure SI unit of energy is a joule. And if a watt is a joule per second, it means a joule is a watt second. Again, look at it. It's a unit of energy because it's power times time. If you want to determine the energy consumption of this device, drawing 2 amps from a 120 volt source over the course of 10 hours in the terms of joules, you'd have to convert 10 hours to its equivalent number of seconds, where 10 hours times 60 minutes per hour times 60 seconds per minute equals 36,000 seconds. Energy is power times time. 240 watts times 36,000 seconds yields 8,640,000 joules, or 8.64 megajoules. No one does this though, because the joule is a tiny, weird, unwieldy unit. Everyone uses unit kilowatt hours for energy. 2.4 kilowatt hours makes far more sense, and it's far easier to calculate. Large generation facilities like dams, wind turbines, or coal-fired power plants sometimes use figures of megawatt hours, gigawatt hours, and even terawatt hours to express unusually large amounts of energy, where 1 megawatt hour is 1,000 kilowatt hours, and 1 gigawatt hour is 1 million kilowatt hours, and so on. On a consumer scale, take a look at common residential appliances like a toaster. Flip it over. Make sure you're over a garbage can before you do this, because I just know you got like 2 years of crumbs in there. There should be a tiny label on the bottom that indicates the power rating of this device. In this case, let's say it's 750 watts. How much energy does it use if you used it for an hour? Not like you'd ever do this though. Energy is power times time. 750 watts used for 1 hour is 750 watt hours. In terms of kilowatt hours, the common unit of energy used by your electrical utility, means we got to place the decimal place over there. So it's 0.75 kilowatt hours of energy. Power figures are incredibly handy in load calculations, given most devices are typically supplied by commonly available voltage values. I know residences in the US are typically supplied by 120 volts RMS AC and not DC, but let's pretend they're essentially equivalent right now. What's the current draw by this 750 watt toaster when it's hooked to 120 volts. If power is equal to voltage times current, current is equal to power divided by voltage. 750 watts divided by 120 volts yields an expected current draw of 6.25 amps. Again, like I said, power figures are incredibly handy. Consider the two extremes of voltage and current in associated power calculations. Consider a switch in series with a resistive load element. The resistance of an open switch is infinite and no current can flow through it. That being said, there is a voltage drop across it. In this case, the full voltage of that supplied by our source. However, with zero current flowing through it, what is the power loss associated with this switch? Regardless of the magnitude of the supply, with zero current flowing through the switch, the power loss for an open switch is 0 watts because there is a voltage drop across it, but no current through it. Charges need to move to carry energy to a destination. What about the other extreme? Consider a closed switch in series with a resistive element. The resistance of an ideal closed switch is 0, and the voltage drop across something with 0 ohms of resistance is 0 volts regardless of the current flowing through it. With no voltage dropped across the switch, and regardless of the magnitude of the current flowing through it, an ideal closed switch will dissipate 0 watts of power. In this case, charges are moving. They're just not dropping off any at the switch as they pass by. All voltage is dropped across the resistor. The ideal nature of a closed switch having 0 ohms of resistance is an obvious oversimplification, but not really far from the truth. When you're dealing with large values of current, this is where the simplification breaks down. Consider a real switch having a tiny resistance of 12 milliohms being used to deliver 20 milliamperes of current. In this case, the power loss associated with a switch is I squared R. 20 milliamperes squared times 12 milliohms, 4.8 microwatts, a very, very tiny amount, and for all intents and purposes, beneath our level of concern. However, consider this same closed switch with 12 milliohms of resistance now being used to carry 16 amps of current. Current being a squared term, we can expect our power dissipation for this switch to be substantially higher than what we previously observed. 16 amps squared times 12 milliohms, roughly 3.1 watts. To again illustrate the squared nature of current, consider 150 amps for the same closed switch with 12 milliohms of resistance. 150 amps squared times 12 milliohms, 270 watts in the switch alone. It is for this reason high-capacity power electronics devices incorporate heat sinks with transistors. A transistor, for the purposes of power electronics, is a switch, and something we'll discuss in much later lectures. A heat sink is a piece of finned aluminum or other heat-tolerant metal simply used to dissipate, in this case, 270 watts of power loss just in the switch. If that heat sink wasn't there, the transistor would just melt and be the source of all sorts of bad. Sticking with this topic of power losses associated with different magnitudes of current, you'll immediately appreciate the reason why electrical power is transmitted using high voltage rather than high current. I know transmission is typically AC and not DC, but let's pretend they're equivalent right now. Let's say you're trying to transmit 2.3 megawatts of power from a wind turbine out in the sticks to a city located in the shoe-wearing regions of the country, and the super long transmission line is modeled as a resistor with 7 ohms of resistance. If you tried to transmit all 2.3 megawatts of power using 240 volts, what's the current you need to accomplish this? Power is voltage times current. Current is equal to power divided by voltage. 2.3 megawatts divided by 240 volts yields the astronomically high value of 9.583 kiloamps, close to 9,600 amps. If power dissipation is related to current squared, you can already see where this is going. The power loss in the line is I squared R. We're taking our close to 9,600 amps squared times 7 ohms resistance would yield us a power loss in the line alone of approximately 642.9 megawatts. Can a 2.3 megawatt turbine produce 642.9 megawatts of power? The answer is no, this is not going to work. What if we use the world's most expensive transmission line, composed of a fat, heavy, expensive silver conductor with only 7 milliohms, or 0.007 ohms of resistance? Even so, with 9,583.3 amps of current cranking through it, you're going to observe a power loss of I squared R, or roughly 642.9 kilowatts. Again, in the line alone, meaning of the available 2.3 megawatt input, roughly only 1.66 megawatts actually makes it to the city, and the rest just goes to heating up the transmission lines. Construction costs aside, you will never build this transmission line, because the moment you string it up, some tweaker is going to climb those towers and cut those silver conductors down and sell them to a scrapyard. The temptation of a 300-mile-long row of silver dollars will be far too great for even a man of my moral character, and I might be up there doing the same thing, only faster, and not getting caught or killed in the process. Now, consider the same 2.3 megawatt turbine transmitting its power using a regular transmission line with 7 ohms of resistance, however, doing so at an increased voltage of 34.5 kilovolts. What is the current necessary to transmit this 2.3 megawatts of power using this higher voltage? If power equals voltage times current, current equals power divided by voltage. 2.3 megawatts divided by 34.5 kilovolts yields roughly 66.7 amps, substantially less than our previous configuration. Now, with 67.7 amps traveling through a 7 ohm resistance, the power losses in the line are I squared R, or 66.7 squared times 7, or roughly only 31.1 kilowatts. Meaning of the available 2.3 megawatts being supplied, roughly 2.27 megawatts actually makes it to its intended destination. By stepping up the voltage, we reduce the amount of current the line needed to carry, and by doing so, we dramatically reduce the amount of power lost in the lines. Can you now appreciate the advantage of high voltage distribution? High voltage means less current for the same amount of power. Not only are your line losses less, you can use thinner, lighter lines less prone to tweaker loss. One more example of the extremes of voltage and current for power calculations before we close up shop, this time one featuring solar power. Consider a common photovoltaic panel, sometimes known as a PV panel. We'll discuss PV panels in detail in later lectures, but for now, think of a PV panel as a current-limited voltage source. When you expose it to different levels of light intensity and hook it up to different electrical loads, you can observe different voltage and current outputs. For the most part, output voltage of a PV panel is temperature dependent, and current output is light dependent. Yes, there are tiny variances in voltage due to light intensity, but for the most part, if it's dark, a PV panel won't produce any output voltage, but the moment it reaches a certain light intensity, it kind of just turns on and outputs a voltage. Voltage varies as temperature increases or decreases. In this case, they're inversely proportional. As temperature decreases, voltage goes up. As temperature increases, voltage goes down. Current is just the opposite. For the most part, output current stays the same regardless of temperature. However, increasing levels of light intensity directly increase current output. Consider the extremes of a solar panel's intended realm of operation. What if the solar panel did not have a conductive path between its terminals? In this case, current would be zero, and the voltage we'd observe is what's called open circuit voltage, or VOC. In this case, voltage is at a maximum, but current is at a minimum, and we'd be right there on our curve. If power equals voltage times current, and our current was zero, our PV panel with an open circuit between the two terminals would be outputting 0 watts of power. Now consider the opposite scenario. Short circuit the two terminals of a PV panel with a 0 ohm resistance path. This is the one occasion you would intentionally short circuit a device because this PV panel is again current limited. Unless you're on a rocket ship and move closer to the sun, there's a certain maximum current this panel could ever produce. But inside the Earth's atmosphere, will never exceed. This current is known as the short circuit current, or the ISC. In this case, the short circuit current is being routed through a 0 ohm conductive path. What's the voltage drop of a 0 ohm conductive path? Voltage is current times resistance. Regardless of the current, if it's 0 ohms of resistance, we'll see a 0 volt drop. Our current might be high at the ISC, but our voltage is 0 volts. So it means we're right here on our curve. What's the power associated with a measurable short circuit current with no voltage? Power is voltage times current. If the voltage is 0, the power is also 0. Again, for conditions of high current and 0 voltage, the power is 0 watts. This is kind of like a closed switch. What we've been doing is considering the performance characteristics of the PV panel at the two extremes of the IV curve, or the current and voltage curve of a PV panel, where the product of the two intersecting numbers is the power output by the panel. Instead of a short circuit or an open circuit between the two terminals of our PV panel, we can place an electrical load where the voltage across it and the current through it, i.e. the product, is the power supplied by the PV panel. In our two extreme scenarios of a 0 watt open circuit and a 0 watt short circuit, we know in between these two extremes, the panel is producing power. It stands to conjecture that our power curve should climb to some maximum, peak out, and begin to fall. This peak value is known as the maximum power point, or PMPP, and it too has associated current values. The voltage at maximum power point, VMPP, and the current at maximum power point, IMPP, the product of which is the nominal power rating of our PV panel. I don't intend to divert this lecture into an in-depth discussion of PV panels, but realize we've already covered several incredibly important topics about solar power in a very short time, notably the IV curve and its response to light and temperature, short circuit current, open circuit voltage, the voltage at maximum power, the current at maximum power, and the power rating of a PV panel. During later lectures on renewable energy applications and solar power at the Big Bad Tech channel, I'll show you how to read specification sheets of a typical PV panel and gain further appreciation of the significance of these figures and how they are used to design solar power systems. Until then, that's all I've got for you today regarding power. The single topic tied together a number of previously unrelated topics. It is entirely understandable and encouraged that you revisit these topics if necessary. Moving forward, realized progress will be predicated upon your synthesis of previously covered material. You've already got an appreciation of how power calculations are directly related to high-level topics like transmission and PV systems, and this level of interconnectedness will only become more important as we progress through this series. In conclusion, this lecture took a close look at the different permutations of power calculations for DC power, sometimes collectively known as Watt's laws. We reviewed power and energy calculations and used the fact that power in always equals power out to error check calculations and troubleshoot basic electrical circuits. We introduced a common device used to measure power, the wattmeter. Additionally, we had a preliminary discussion of the importance of power calculations related to the transmission of power and alternative energy sources. Remember to review these concepts and practice these techniques as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.